hold. It needed proper isolation of environment, and another one is test all. I don't really know what it is about, except the test says that there is a safety margin set to an arbitrary number, and that arbitrary number is just not arbitrary enough to include Fedora.
Oh, so should we use this time to look at that?
That one Victor is looking at, and I really don't know where he's at.
Ah, okay.
So not entirely sure, but I guess we could. Would really be that bad. So, like, let me just find it. What was this string?
So there's a safety margin. I think it was 25%.
No. Let me.
Test call.
Test margin is sufficient. Yes, this one.
So when I backported this to 314, I think, I made it extra 20% instead because it failed on something.
I did.
And I'm not sure if that's because of something that's been fixed in 315 or not. Fun fact, the code that this is testing has a bug for which we're adding new API to Python 3.14.1, which is like really weird, adding new features in a patch release. So yeah, would you like to understand what this code does?
Sure.
Okay. So this is about recursion errors. So if you have a recursive function in Python, there's a counter that counts up, and when it reaches 1000, it raises a recursion error. That's just very simple. If that counter wasn't there, the recursion would just consume all of your memory and just work. If you're only calling Python functions, because calls from Python to Python don't use the C stack. Do you remember what the stack is?
Okay. So it's a chunk of memory where there's heap and stack, and one of those is managed by the C program itself, or like whatever runs it, and one of so your custom things are stored in one of those, and the things that you the global variables and everything is in a different one.
Right. So well, global variables are a completely different area. Okay. But there's the heap, which is where you allocate memory using malloc and things built on top of that. And then there's the stack, which contains local variables and return addresses. So when you call a function, the current address gets written to the stack. Then a bunch of new memory is added for the local variables. Function is called, and when it returns, it reads the destination where it should jump back. So there's actually a file in internal docs about stack protection. Right. So traditionally in C, if you have a pure machine and no operating system and just all memory is yours, you could do this by saying that the bottom of the machine stack is at address 0, or at some, leave some space for system stuff, but at a low address. No, sorry, no, okay, other way. The top of the machine stack is at the end of the memory, right, at the highest address you can have, and it grows down towards 0, right? At the other side of the memory, at address 0, 0 is special, then you would have some global variables, and then you would have the heap. So if you call malloc, it would do pretty much the same thing, but it would grow from the low memory up, and it would just use as much memory as it wants. And as soon as the stack meets the heap, you're in trouble, because things start overriding, writing into places they shouldn't. And the problem is there isn't very much protection against this. It's called stack overflow. There isn't too much protection about around this in like Linux and Unix systems. So Python has stack protection itself. And the way it's done, so Python has stack protection because you can call C functions from Python, and those use the machine stack. And there's always one entry for whenever you call Python functions, however many you call, there's one entry on the C stack for those. Nowadays. It wasn't always that way, but that's how it is. So originally, just a few years back, Python had this API called PyEnter recursive call, which is a function that you call when you enter a C function that could recurse. Right? And there's also leave recursive call. And this worked pretty much the same way as the Python recursion protection. It would increment a counter. When that got too big, it raises a recursion error. So what it does nowadays, after a bunch of changes to the mechanism, is it actually looks at the current stack pointer, at the current position in the stack, and it sees if it's near the boundary, near the bottom of the machine stack, like the bottom of the reserved memory. Right? So again, there's nothing really in the operating system that prevents the stack from growing out of this bound. So we find out where the bottom of the machine stack is. We leave something for something as a margin for a so-called hard limit, and something as a margin for a so-called soft limit. Right? So when this enter recursive call or functions like it end up being above, or well, below, because we grow from the top down. So when we're below the soft limit, it raises a recursion error. problem is Python code can catch the recursion error and call more C functions. So if you do that too much, there's a hard limit, and if you're in this hard limit area, it's a fatal error. It just kills the process entirely, which is a problem. So that's what this is about, and this test call will get the stack pointer, assert that it's less than the lower. Get the stack pointer, then get the stack pointer inside a function, a Python function that's called by CPy, so it gets a C stack entry. Assert that the one is lower than the other, and it asserts that the difference between these two pointers is low enough so that if you imagine all the entries on the stack being for Python functions, you can't skip this soft limit area. Right? So if you call a Python function right here, just above the soft limit, you will land in the soft limit area. You won't skip it entirely. Like the Python calling, which is like the biggest function in CPython, won't just go directly to the hard error. It will raise the recursion error, right? So yeah, that's pretty much what that does. And yeah, obviously this is very platform dependent. We can look at the code that does this. Where is it though? Now there's region recursion. Yeah, it should be in CEval 4.6, somewhere around there. Yeah, there's this set recursion limit. That's new recursive call unchecked. Oh no, this is Python recursion. Sorry. Where's stack lines? Okay, here it is. Initialize recursion limit. So this is the function that initializes the thread state, like before you call any Python API on a thread. It will get the hardware stack limits and set the stack top, hard limit, and soft limit based on those. And there's this margin, which we saw in the diagram. There's another margin, and then there's this. Yeah, there's a top and there's the base, right? And these two things we get from the operating system. So there's something for Windows, something for Apple, something for glibc, and like anything like glibc, and something for all the other systems like this Alpine Muscle, whatever. And this is pretty problematic because this works like the fallback where we don't know what the platform API is, or there is no platform API. We just get the current stack pointer and add a number to it, and that number is an educated guess. Right? There's one for S390. There's one for Windows, where we always ask the OS, which I don't think is correct, but we do. And there's, Android, Spark, whatever, and the default. So yeah, that's just a guess. Right. Oh.
So in a way, it's just expected to like hit the corner cases.
Yeah, if you hit the corner case, you let us know and it gets fixed. So where is the corner case? Do you have the Fedora bug?
I don't have. I have the. I've got the result from the test. I can paste it to the chat. So the second assert, the one that asserts that safe margin is lower than the stack margin, gives the
right.
situation. Yeah.
So safe margin. So this is the difference between the pointers times 25%. It should be lower than the actual stack margin. What machine is this?
I will tell you just in a moment, hopefully. Will I? Let me paste the build that failed, and I'm going to look at the logs. Will this tell us? Like, it should be x8664, but you never know for sure if that was the builder that was acquired and that emulated the environment.
I updated Fedora and all my monospace text is not monospace.
So you're on the for 43 now?
Yes.
Oh wow.
So monospace is monospace working?
How is Python on Fedora 43?
I don't think I've actually used the system Python so far myself. But DNF worked.
That's a good sign.
I'll get to all the broken vents later. So test call. Okay, what machine is this? How do you configure? Configure, build. Wow. Everything gets in there, right? Directories. Oh, LTO. Huh. So this is with LTO, with debug, and with Volgrind. So this is all of the debug options on. The Volgrind might be an issue. And there's dtrace as well. Haha. Let's see. So pydebug, no ensure pip. This is Fedora stuff. Let me not do the LTO right now. So we have dtrace volgrind pydebug. this and try. Okay, that works. So let's put the LTO back. It was test call, right? Yeah.
I have this build failed on all Fedora supported architectures and the numbers are different.
No, I didn't want to clean. That also didn't fail. So I guess we enable the JIT as well. Do what's disable dependency tracking?
There's a warning on that just under the configure that the option doesn't exist. So,
okay.
Kinda, I guess it does nothing. Just looking at it.
It's probably something added by the Fedora build system, right? Oh, there's enable shared. And computed go-tos, I think, is the default, hopefully. Without static libpython, it shouldn't really affect much. I wonder if this stream should be renamed to, like, Python Fedora office hours.
Maybe.
Huh. I probably need LD. Library path when enable shared is on, because otherwise I can't use Python inside the build. No? And maybe I need Python for build, right?
I have never seen this environment variable, Python for build.
is a Python for build. Maybe it needs to go and configure. No. Oh, I just...
Why 3.13 though? Like the main Python for you right now should be 3.14.
And I guess my Python 3.13 isn't installed. That must be the system upgrade. Okay, let me install the libraries for Python 3.13.
Okay.
Ah, there we go. And it can't find CLang 19. Build dep is something I haven't done yet. And
so CLang is a conditional requirement for JIT.
Is it this stuff? Yeah. Okay.
The issue with it not being included in build deps.
Victor is probably much further in this investigation, but it's still hopefully interesting.
It is. I'm so always surprised, but also it's insightful to see how you debug issues, because you just have better intuition as to what can be the next step, and seeing how you hack around the issues you encounter is great for me.
Oh. Well, hopefully we'll get to the point where I just have different intuition. Alright, it's built. Now we test it. Build some stuff again. And succeeds. Wow.
Nice.
Okay, I think I've cherry-picked everything from this configure. That I could. I mean, does Red Hat Linux do something differently than whatever I have? How did I configure this again? Build and host. How did build and host get in? Okay, so let's configure, and then you make With O0. Ah, that might be interesting. C flags noticed shouldn't. Oh. Oh yeah, this will be interesting. And here's Python for regen. I think that's part of the Python for build.
Mm-hmm.
Okay, that didn't help. So let me remove everything except for the config cache and make with, so extra C flags is O0, no C++ warnings, C flags noticed. There's debug info, fortify source, hardened specs. Something in here could probably increase the size of the stack entries.
Mm-hmm.
And I didn't configure it right. Looks like all of that is being passed to GCC. There we go. Okay, so it's something in the make. Yeah. So, so I will need to bisect this. So clean everything. I'll try removing everything that looks Red Hat specific. So I'll configure like this.
Mm-hmm.
I need to clean everything for configuring like that. And I'm making notes of how I'm building stuff so I know what to do later. So okay, GNU source. Architectures. So let's remove NOBin. Red Hat hardened stuff. Something is causing something to wait. Yep. That did something, so it's an upstream bug, most likely.
Right.
What is the next thing? That could be good to remove. I guess all the warnings. So let's see. I'll remove static lit Python and with computed go-tos. And maybe even the experimental JIT. This takes a lot of time. So warning options go away. So no CPP. That one will be next. glib cxx assertions. I'm not sure what that does. Errors, warnings. Let's try that. What is taking so long? So I'm kind of compiling. Not still bad.
Good. It's still bad.
So let me remove the O0 now. This was just warnings as well.
O0 means no optimizations or the strongest?
No optimizations. that failed as well. Let's remove LTO now, because that takes a long time.
What's LTO?
Link time optimization. And this was the make command, so there's FLTO, fat LTO objects, those look LTO related. So normally in C, each C source file gets compiled into some kind of binary object, and then those get linked together. And link time optimization will then, as part of linking, try to optimize things like function calls. So if some function is called a lot and it's small, it will inline that function even if it comes from a different translation unit. It was LTO, or at least part of it was LTO. Which makes sense. This link time optimization will generally do fun stuff with the stack. Okay. So we need to go back to including LTO. So what else? Maybe volgrind and dtrace will go now. And that succeeded. Okay. I'm forgetting to take my notes on a separate screen. So it's either volgrind or dtrace. Let's try disabling volgrind first. That was fine. So let's try disabling dtrace.
Without LTO still.
Oh, I was... Right. Sorry.
Okay. I thought it was missing, but I didn't have.
I need LTO. Yeah.
Yeah.
Okay, so let's remove dtrace but keep LTO.
That removed wall grind, I think.
Right. Dtrace and LTO.
Mm-hmm.
Make. Okay. So dtrace is not it. Let's try wall grind. I hope I'm not caching something somewhere. I hope my notes are good. But dtrace, wall grind and LTO seem like reasonable culprits. So let me try that again. Dtrace, debug, vol grind, and LTO. With this giant make. And that succeeds. Oh.
Oh, the worst, the worst.
Okay, clean everything and run it again. The thing that failed last. So dtrace, vol grind, LTO, enable shared. Then make, and I'm keeping the O zeros there as well. And that fails. Okay, so should I remove the O zeros and see what changes? Except I need to clean everything. Which this takes a long time. So without O zeros. And that succeeded. Okay, so it's O0 combined with something. Is it just O0? So if I remove now, let me just have vol grind, dtrace, and LTO. Without even the enable shared. And then clean the make as well. I think I need fpick. But let's get rid of GNU source. What is this? No omit frame pointer and no omit leaf. Oh, there's leaf here. Yeah, the frame pointer might be interesting. I'll delete dialect. There's some stack clash protection that might be interesting. Asynchronous unwind tables, I think that's for C++. Let's remove the tuning, architecture. Maybe let's keep the stack protector for now. Ellipse assertions. Fortify source might be interesting later. I have no idea what pipe is. GCC switches. Let's remove that. Debug information. Let's remove that. Exceptions.c++. So let's try with this. Oh, and that doesn't give the O0, right? So I need to put O0. Fortify source requires compiling with optimization.
But we had it disabled.
Ah, but maybe in the cflags noticed only. Huh.
So there is O3, which is then, I guess, rewritten. In the first line of the invocation to GCC, there is O3.
Oh. Where did that come from?
That, who knows?
Wow. So this still fails. So let's remove LTO for now. And then remove the fortify source stuff. We removed LTO, so get rid of those as well. Next time we should remove the stack protector. And that fails. good.
Oh, the number was completely different though.
I guess some of these options do have an effect. That was the Fortify source, right?
Mm-hmm.
Okay, what do we remove now? The leaf pointers, the frame pointers, and stack protection.
Mm-hmm.
So we only leave fpic and O0. And that failed. Is the number getting bigger?
Yes, it is bigger than it was last time. So the safe margin decreases as more options are added.
So that was just dtrace, volgrind, and fpic O0.
Mm-hmm.
Do we only need O0? Yep. Okay, so that was configured with nothing and made with just O0. So if you disable optimizations entirely, this test will fail.
Mm-hmm.
So once again, I've cleaned everything. I do a configure. And make, and I guess I can set cflags to O0. Not cflags noticed. Yep. Okay, well, that's for an upstream bug report. And my internet doesn't work. So I guess it needs a, well, is anything closed here?
I was looking for the exact test name, the margin, whatever, and I didn't find anything.
Mark Shannon's issue that caused all this. Implement stack protection for supported platforms. Custom frame evaluation, that'll also change the stack limit. Somebody asked Mark on June 8th.
23.
23. Yeah. Mark just doesn't care. So what's this? Just call.
It has failed on all Arches Fedora supports. So yeah, different numbers, but none was successful.
What is this? Bug and might be Linux, but who knows? What's the right tag here? Interpreter core. Okay, well, thank you for finding this bug.
You're welcome. Always in service. We will skip the test for now. It does not block us.
Yeah, skip it. I'll get... Hopefully it won't cause any issues.
We'll see.
Right. Well, that's all the time we have.
Yeah.
So thanks and see you next time.
Debugging. I've got a couple repository with the NF5 built with stable ABI if you want it.
Nice.
We'll take a look at next time.